Hello everyone, welcome to your next class. Today we are going to spend all of our time on one type of machine learning model known as random forests. Random forests are an excellent way to start learning about how machine learning processes go because they're generally a very simple concept. I don't need to show you a lot of math in order to show you how the process works. Also, random forests are extremely robust, so you can use them for all kinds of situations. Either categorical data with continuous values, with interval or rational information. It can be used for virtually any type of data. So it's a really nice jumping off point for machine learning to show you, how the steps in one type of machine learning process work out. So today what you're going to learn is you're going to learn some high level concepts of how random forests are running. We're going to show you what decision trees are and how decision trees work. So there's going to be a handful of definitions that you're going to have to understand in order to get through the rest of this lecture. And also I'm going to show you how to run a random forest model in under like 10 or 15 lines of code. It's going to be very basic and for a very specific type of data, but you're going to see how this all looks at least from the ground up and get a sense of how you would build a random forest of your own for your own data or interests. Okay. So why don't we just go into it? So definitions, we are going to talk about decision trees a lot, and what a decision tree is basically it looks like a bunch of branching paths that have classifications next to them. So the point of a decision tree is that what it's trying to do is it's taking a bunch of variables and determining if it could figure out classes or subclasses within those variables. And so what it starts with is like a large set of variables and a choice between one or two things, and determining which variables are most important for making that classification between those two choices. And we call that a decision node. It's where a node, a point in our decision matrix, where the node splits into two different choices or two different sub-decisions that it can make, okay? The terminal node is where, at the very top, where the nodes don't, or pardon me, it's at the very bottom where there is no more splitting at all. So at the very bottom of our tree, you'll see these things called terminal nodes. The concept of splitting is the process of dividing up a node into different decisions. And the concept of pruning is where we take a decision node and evaluate whether or not it's useful to have it in the first place, and eventually we decide if it's pruning, that it's not valuable, and we remove it. Okay, so I know these definitions seem a little bit abstract, so why don't we show you a decision tree itself, and we can go into this thing one at a time. So you're actually gonna build this, guys. What this is remember the iris dataset we've been working on? This is a decision tree for the iris dataset, trying to separate it into different classes and species. We'll go through the code on how to do this in a moment, but for now, let's actually go into syntax, and I can start breaking down those terms and definitions that I was telling you about just a second ago, okay? So we're going to move into syntax. We have two syntax sections. First syntax section is going to talk about the decision trees and how they work and using those definitions on the graph itself. And then the next one is going to show you the code that we did in order to generate that graph, okay? So let's go to that now. So first things first, here is our decision tree. You can obviously recognize some things here. We have petal length, we have Virginica, Setosa. So we have all of these, the different classes, petal width, that show all of these, this decision tree, basically. What you're seeing are 5 lines of data here. First is the petal length being less than or equal to 2.6 is what the decision tree is determining, or creating the decision node across. So if it's less than or equal to 2.6, it's going to this node, which is a terminal node. It doesn't have any other decision nodes coming out of it, as you notice. And then you have the false, where it's greater than 2.6, and you have all these other tree branches going on, where, okay, it's still Virginica, so, okay, less than or equal to 1.65, that's where it's going to split between Virginica and Versicolor here, okay? You'll also notice that this number is this thing called Gini. Gini is a measure of disparity or distribution of, it's almost like an income or inequality metric. That's where it started. It started in economics. We use this measure to determine how much money is distributed in a small group of people versus like the population at large. An example of this would be the 99% movement. They would be arguing that people in the US or whatever have an extremely high Gini coefficient, meaning income inequality is very high. But Gini is also used to say like how data is dispersed among itself, and is it clustered all within like a very small group of samples. So higher Gini, more unequal the distribution is of certain values, okay? That's all you really need to know about it. The values here, you don't need to really worry about what these values mean. This sample says how many samples it took to create this decision, to create this split, basically. See, 33, 63 equals 96. And it tells you the class of the flower here. So this is our terminal node. This here is what we would call splitting. This is the process of splitting this data set into two different groups. It split it by about a third because 33 went to our terminal node, which doesn't have decision nodes, and the other 2/3 went to another node which did have decision nodes. Let's say that this Gini sample, like, okay, so we have a subsample here of 1. That might mean that, okay, this is like way too split, and we would want to prune this for perhaps. So that would be what pruning is. This again is a decision node. This is a terminal node. This is splitting, and this is pruning. So how this whole process works, guys, how a random forest works is, remember our iris dataset had petal length, petal width, sepal length, and sepal width. So what a random forest does is it selects a subset of these variables and then determines, and then we also have the labels for each of these pieces of data. So we know the sepal length and width for every flower in our sample, but we also know what it actually is. So it takes, a random subset of variables and sees if it can determine, split the differences between these groups based on this subset of variables. The more it can, the more it's going to more prone it's going to be to actually create a splitting and create a new node. And the less similar it is, the more inaccurate, or like the more it can't really tell the difference between the two classes is trying to find, the less likely it'll split. And it'll take a random assortment of all 4 of these or n variables, depending on how many you have in your set. And it does this process over and over again. So it'll take 2, maybe sometimes it'll take 3, sometimes it'll take 1, sometimes it'll take 20 if you have that many variables. But it'll then select these and then run through this process of seeing if it can split here. And if it does, okay, then it'll see if it can split here. And calculating all of those and trying to figure out the optimal splitting based on the variables that exist, okay? So you can see how this can be used with both ordinal data or even, interval. We sometimes call this categorical or continuous data, okay? So that is the basics of a decision tree and how the process works. It's really not using any math. The point is to show you how it kind of like, how the machine learning model is actually trying to think, I say with air quotes. Okay, so with that, let's move into our next image. Where is it here? Here it is. And this is all the code that we need in order to build that graph that you saw, guys. It's really simple. It's quite amazing, isn't it? So here we are here. Oh, that's a bit thick. Let me adjust the size of this. There we go. Yeah, much better. Okay, so first set of code. This first line is where I got the code for this, guys. It's on a blog, but it's free to use, and all the data is free as well. So it's really nice and simple. So I figured it was best to just use their example in this. So one thing you're going to need to download You should have scikit-learn already, but you might need to install GraphViz onto your computer. This is not a Python package. This is basically a graphical visualization software. If you just Google search GraphViz and go through the install process from the website, super easy, and this will work for you. So first thing we do is we load our iris data set right here. That's all that's doing. Pretty simple, right? And then we load in our random forest algorithm, okay? We then create our classifier and say that we want it to try and estimate 10 different splits. Okay, so we're gonna play with this number a bit when we get into our code. We say, okay, and that's the only parameters that we're giving our random forest. There's a bunch of different parameters we can tune in this and say like, oh, we want it to learn this fast, or we want it to ignore this. But we're really just trying to do a simple thing here. So from this iris data set, even though it's .data, it's like its own object. You can basically what the model.fit is doing is you pass in your x and you pass in your y. Okay, so if you had labels that aren't this iris object and you had data that wasn't this iris data object, that's how you would do it. Okay. The last thing we then do is extract one tree. This is just a sample tree that we are then going to visualize. Okay, so we then from our scikit-learn, we import their graphics visualization function, and we pass this information into it. We give it one of the trees we want. We tell it the out file for for GraphViz's like syntax for it essentially. We tell it the names and the classes for the model. We round our data and we add a couple other parameters here, like filling and how precise we want the numbers to be, and so on. Lastly, we import this thing called call, which is going to convert our GraphViz syntax code file into a PNG. So we say, you know, this is coming out as a dot file, a dot file. You don't need to know what that is, what a dot file is. But we say, okay, we have a dot file here. We want to turn it into a PNG. The file path is called .dot. We want to use these, use these parameters. We want to turn it into a PNG, or we want to call it this file, and then we want our GDPI to be of 600. Okay, and that's all we're doing in order to build this graph, guys. It's really quite amazing how simple this is. Okay, so why don't we hop into our Jupyter Notebook and just get this, start playing with this and see how it all works. Okay, here we are, guys. Let's start playing with this. First thing, I'm going to run this and see how it all runs. Does it still run? Runs just fine. You can't really see what just happened here. So maybe we can just look at the model really quickly, and then we'll play around with a few stuff to see what kind of images come out. Let's just try print model and see what comes out. Okay, so it tells us the parameters of the model here. Not bad. We can look at iris.data if we want. Iris.data. That's what iris.data is. Look at it's our petal. I'm not sure which order it is, but it's our petal length and width and our sepal length and width. But all of them are consistent across this data set. So that it's almost like a column of data. But you'll see here that X is really just a list of values, okay? It's 4 values, and then let's see what target is. And then it's just these labels, 0, 1, and 2. And what these binary things mean are essentially it's our features. Is it Virginica, is it Versicolor, or is it Setosa? Okay? And we're just labeling them in a binary way, and then we convert those labels back into English later on because our machine learning models, even though this is a number, it's still technically categorical data. We're just assigning a different label to that category. Let's see if we can print the estimator. Shows all that there. Just shows all of the random state and a couple other things there. Let's see if we can print this and what comes out. Is it maybe just that object again? Oh, that's what happened. I put in estimators twice. Model.estimators_. And ends up printing the same thing. So that's what's going on here, guys. This set of code isn't going to output anything for us. It really is that PNG at the end, okay? So I'm going to just adjust one last thing here. I'm going to half the amount of estimators and call this tree underscore 5 and see, and we'll call this tree underscore 5 as well, and see if our graph looks any different. List index out of range. Interesting. Okay, that's what's going on here. So we have 10. Let's put that all back. We have 5 there, and let's just go with that there. That should work. There we go, and that output. So let's see if we can find tree 5 and what it looks like. Okay, it is a little different. Look at that. Here you have that here. Here's our new tree that was looking for 5 choices, and our other tree that was looking at 10. And they are different. Oh wait, this ends up the same. Oops, that was not the right one, guys. That tree obviously looks quite different than, you know, this one here. Okay, guys, with that, let's recap here. We learned what decision trees are, how the basic functionality of a decision tree works, how we build that process. We showed you how to run a simple random forest and how to graph it as well. So with that in mind, guys, thank you very much and catch you next time.